Hello everyone, welcome to digital image processing of remote sensing data, and we are going to discuss in 20 lectures different aspects of digital image processing. But before that I would like to discuss what is exactly a remote sensing image and how it is represented. So in this particular lecture we are going to discuss in detail about this digital image, in a spatially digital image generated by remote sensors. As you know that a picture tells 1,000 words and a satellite image can tell 10,000 words, because not only you are seeing the satellite image, but the interpretations and inferences which you make out of satellite image are much more important and more useful. So that is why it is said that a picture tells 1,000 words or a map tells 1,000 words, but a satellite image tells 10,000 words, because of capabilities of one can perform interpretations as well as can take out some inferences. So what exactly an image is? So if we look the definition, an image is a pictorial representation of an object or a scene, and when it is there are various ways of taking images. As we know that nowadays most of us are having digital cameras in our mobile or otherwise DSLR and other cameras, and all are collecting images in digital formats. So they are all digital images. But the difference between these digital images which are taken by handheld cameras or mobile cameras and satellite cameras are different, and which we in due course of time we will be seeing the differences between these two. And secondly, earlier there used to be a film cameras, so we used to call a photograph. So there is also some difference between an image and a photograph. So those things we will be also seeing. Earlier, because the photographs were on the films or negative films, and then positive prints used to be taken out, still some people like film cameras because of high spatial resolution, but these are the analog, not digital. And digital, as you know, that it will have a two-dimensional matrix, which we will see in detail. Analog images examples produced by photographic sensors on paper based on media or transparent media, and that is typical example of film cameras. And variations in scene characteristics are represented in variation in brightness or gray shades. This is common characteristics both in analog images and digital images. And the objects which reflects more energy appear brighter on the image, and objects reflecting less energy appear darker. So these are the ways an image can be created, analog or digital. Now digital image which is produced by electro-optical sensors. So the image which has been created or data which has been created by such electro-optical sensors, then we call them digital images. And as you know, the unit of an image is a pixel, so which is arranged in a two-dimensional matrix. So a digital image is nothing but a two-dimensional matrix. Each cell or unit of this image, digital image, is a pixel. Pixel is an abbreviation which is also called a picture element. So smaller the size of pixel in an image, that means the area which is representing, we say high resolution. And the high resolution otherwise we understand by number of rows and columns for the same area. So if I say 8 megapixels and 12 megapixels, then 12 megapixels is having higher spatial resolution, because number of rows and columns will increase, and therefore number of pixels within an image will increase. Thus area which each pixel will cover would be less in high resolution images compared to relatively low resolution images. And each pixel is associated with a number, a digital number, or also brightness value or pixel value. And if it is black and white, that means say if suppose it's a 8-bit image, then we can also record in gray levels, or we can bring in color form as well. So this is the unit is also very important. Another important thing, the unit is always square in shape, which has been mentioned here, that the equal size is square pixel. Now it is one important thing here is the unit is square, but overall size of an image can be either square or rectangle, which we will see little later in much detail. And as mentioned earlier, that any object which is present on the surface of the earth, now we are talking more from remote sensing point of view, that an object reflecting more energy records a higher number of itself on the digital value. So the pixel value would be higher, and if a object which is darker on the surface of the earth will record a very low value, and vice versa is also true. So it is there are various types of data which we understand. One is raster, another one is vector or tin, as I have discussed in the other two courses. One is in remote sensing, introduction to remote sensing, and introduction to GIS, in which raster, vector and tin and other models have been discussed. So image is a raster because it's a two-dimensional matrix, and each cell here we call as pixel is a square in shape. It is a two-dimensional matrix, and the unit is a square, and which we call as pixel. As I have already mentioned, that overall image can be either square or rectangular in shape. And now we are seeing one example of here, that let's take first this digital matrix here. This is a two-dimensional matrix, and each cell here, though line, the black lines and rows are shown here, but in actual image these lines will not be there, and you will have only these cells or pixels like this on the left hand side. So if we see here that a pixel value which is having very high pixel value 255 is the brightest pixel in a 8-bit or gray image, whereas a pixel value when it is equal to 0, then you end up with the black. So these are black and white in a gray image, and this example of 8-bit image, so we can have maximum 256 shades of gray if we are representing in gray color or gray shades, and so the minimum value can be 0, maximum value can be 255, and rest of the values will fall in between. So both examples within this image is given, that 0 representing the black color, one extreme shade, and 255 is representing the white, which is another extreme, and in rest of the values are in between. If I take example of say 136, then 136 having a dark gray and other thing. But because when we really zoom in, then only we see individual pixels. But if we don't zoom too much, then we can see the overall image as example here, and later some examples will also be discussed. There are a few more important fundamentals which I want to bring here now. Is the origin of an image is always on the top left corner, whereas if you recall in GIS course, those who have gone through that or otherwise, then in that, like in maps, the origin always in the bottom left. So that's the difference, and this plays a very important role when we go for georeferencing, which we will be discussing in this course. So origin is important. Origin of an image is a raw image is always on the top left corner. So the first pixel, and likewise a number of columns and number of rows are there. So there are different terminologies which are used. So for this we say rows or scan line, because by the satellite sensors we scan individual lines, so we call as scan lines, or these are the columns which you can see here, and also we say pixels. So either we call columns or pixels, rows or scan line. Scan lines means we are talking about the horizontal lines, rows, and if column or pixels we are talking vertical lines, and this is definitely a two-dimensional matrix. So pixel values, the magnitude of an electromagnetic energy captured in a digital image is represented by positive digital number. Now pixel value has to be a positive integer value. It's a whole number. It cannot be in decimals, so that means it cannot be a floating point or real number, and you cannot have negative values as well. So a pixel value is always a positive integer. These are the requirements for a two-dimensional matrix. So that has to be remembered in case of satellite images. But overall raster, there are different types of raster in which the cell value, not pixel, the pixel value has to be always positive integer value, but the cell value in other raster like a digital elevation model, where value can be in negative or positive, or value can be integer or real value. So those values are possible, but not an image, whether it is image taken by a camera on mobile or digital camera or taken by a satellite. All the time the pixel value has to be a positive integer value. Now if an image is just a binary image, then you are having two extreme values, 0 and 1. So 0 you can assign black color, for 1 you can assign white color, so that we also call as binary image. Now pixel is a short abbreviation for picture element, and this we have already said. I have also said that pixel is an unit of a digital image, and cells are sensed one after another along the line. So when these sensors on satellites, when they move, they capture the data line by line, pixel by pixel, and record the whatever the brightness values in daytime or in night time if they are having thermal sensors. So whatever the emissivity, any object above absolute 0 will emit energy, and that can be recorded by thermal sensors on board of different satellites. All satellites, all sensors, they do not have thermal sensors inbuilt, but some satellite like Landsat TM or NOAA HRR, they are having thermal sensors, so they can even detect the the emissivity, or which you can convert to brightness, temperature, and ultimately to land surface temperature. That is recorded, that emissivity is recorded, or brightness, temperature. So in the sensor, each cell is associated with a pixel that is tied to microelectronic detector, and each pixel is characterized by some single value of radiation, maybe reflection or maybe emission, and depending on the type of sensor. And I am taking one example here, that like a 1-bit image, so also we call binary image. The total number of pixels we can have 2, that means variations in the pixel values, either 1 or 0, so total 2, and the values can vary between 0 to 1. If we go for the 6-bit image like IRS 1C pen 1D pen sensors had the 6-bit images, that means the values 2 power 6, and total number of values on an image in that was the 64, that values can vary between 0 to 66, total number will be 64. In a 7-bit image like in list 3 image of IRS-C or even IRS-D, then the total number of pixels values which can vary, total is 128, the values were varying between 0 to 127. Generally, a lot of satellites, generally they acquire the data at 8 bits. So this is the most common, you can call as a format for image capturing, 8-bit images. Total numbers are available 256, 2 power 8, and the values can vary between 0 to 255. The example earlier I discussed was of 8-bit image. Nowadays the requirements are increasing. People are going for higher and higher radiometric resolutions, and therefore they are looking, instead of just 8-bit, they can go even for 16-bit or 24-bit, or in between 8 to 16 like NOAA HRR, which records the data at 11 bits. So you will have a different total number of pixels values and range also. Like in case of 16, 2 power 16, so 65,536, and the values can vary like this. So as you go higher and higher in bits, the availability of total number of shades or colors increases. So the maximum number of brightness levels available depends on the number of bits used to represent the energy recorded. Higher the bit, it will give you the better clear picture. Lower the bits, like in binary image, you can have only black or white, not in between values. But if you are having 8-bit, there are 256 shades can be used to represent an area or an image through an image. So a sensor used 8-bit to record the data. There would be 2 power 8 equal to 256 digital values available, and ranging from, as mentioned, 0 to 255. 8-bit is the most common bit value in satellite images. One of the examples here, this is not actual acquired, but it has been simulated or created just for understanding that the image, the same area has been captured at this is 1 bit. 1 bit means binary image, so we are having values only either black, that is 0 pixel value, or white, that is pixel value equal to 1. Whereas 2, then you know that we can have more number of pixel values, and we are having example of 8 bits where the minimum value can be 0, maximum value can be 255. Now visually you can compare the quality of an image. So obviously compared to 1-bit binary or 2 bits or 4 bits, 8-bit image looks much better. If we would have for the same area say 16-bit image or 24 bits image, then definitely that image would look much better. But all the time just improving the bits, number of bits, may not improve the quality of an image. Quality of an image also depends on spatial resolution, which we will be discussing in later lectures. Also, as a color, sometimes we use the 256 colors or say, so that has to be also understood at this stage. As you know, in order to make colored images, 3 primary color has to be added. In case of satellite images, what we do, we assign different color channels to different bands of a sensor. Suppose I take the example of Landsat MSS. Now Landsat MSS is having 4 channels. Out of these 4 channels, I can use 3 channels which are having completely different signatures of different objects which are present on the surface of the earth, and assign them 3 colors, red, green, blue. And once we assign, these will be represented like this. But when we use the additive color scheme and use this like is shown here through 3 circles, then we can create a colored image. Now here it is written that infrared false color composite, because we have used one channel which is NIR, means near infrared channel, in which the vegetation is having high reflectance. And when we assign the red color to that channel, then in this false color composite, the vegetation, healthy vegetation which is having high chlorophyll content, will appear more red. And therefore it is also called false color composite, and the vegetation will appear red. But in normal cases, we don't have the infrared channel, like in our digital cameras. We don't have infrared channels, and therefore you see the colors which are near real colors which we see from our own naked eyes. But the sensors are capable of not only covering the entire visible part of EM spectrum, which we will see in much details, but it also covers infrared, thermal infrared, even in microwave region as well. So when we want to combine and create color images, we have to innovate some other ways, because these are not true color images. And why we want to do it? Because it will give us better interpretability of an image, and therefore better inferences can be taken out from these images. That is why such schemes of false color composites are followed world over. This is the standard technique of creating a colored image from satellite data. One channel which is infrared, representing infrared channel, always assigned red color. Now here the example from our IRS list 2 image, very near to Roorkee, is a Paonta Sahib, which is in Himachal Pradesh, just bordering Uttarakhand, and as you can see that this is band 1 and the band width is also given here, and as see that in different bands the image will look completely differently, and a zoomed part from the corner of the image is also shown through these pixel values. So pixel values vary lot in different channels because the responses of different objects which are present on the surface of the earth in different part of EM spectrum will have different responses, and that is why their pixel values will also vary. Like in band 4, which you are going close to the infrared or near infrared, there the appearance here is completely different. So where water bodies or that areas are appearing as darker, in other images like in visible channel here, they are all appearing very bright. Vegetation, as you see here, vegetation is appearing very dark here, the healthy vegetation, but in near infrared they are appearing little brighter in this image. So this is how the satellite records the data, multispectral data. Now resolutions, few terms I have already used, spatial resolution, but here for completeness I will define it. And so there are 4 resolutions. One is spatial resolution, spectral resolution, temporal resolution, and radiometric resolution. So all 4 we will discuss one by one very briefly. So first one is the spatial resolution. Spatial resolution is that ability to distinguish closed space objects on an image. Higher spatial resolution means larger the image size in terms of computer memory, but more clarity in the image. The quality of image will always be better, but same time there is a trade-off. That means it requires more space to be stored, and definitely in satellite images or in normal digital cameras like in mobile, we are going for higher and higher spatial resolution. So 8 megapixel we talk, 14 megapixel we talk, 18 megapixel. So you go higher the value here in megapixels, we are talking higher spatial resolution, because for the same area in earlier, like in a 2 megapixel, you might be having 1 pixel to represent a large area. Now you might be having 16 by 16 pixel to represent the same area in a large higher megapixel images. So spatial resolution will definitely improve the quality of the image, but as I have mentioned, there is a trade-off. You require more space to store these images either on your flash card or hard disk or any storing device. The second resolution, which is spectral resolution, that is the width, location and sensitivity of chosen lambda bands. So this is the band width where it is there. So if I go back to one previous slide, here the band width are given here. Like for band 1, in case of list 2, IRS 1V list 2 image or sensor, the bandwidth is between 0.45 to 0.52. Whereas here the bandwidth is different. So this is what I am discussing. The narrower the bandwidth, higher the spectral resolution, and broader the bandwidth, lower the spectral resolution. So here it is little different than spectral resolution, than spatial resolution. So here where it is located, what is the width and the sensitivity of chosen lambda bands. So in the visible or in near infrared, the bandwidths are different for different sensors. In thermal infrared, generally bandwidths are quite wide compared to visible and infrared, because the sensitivity in that part of EM spectrum, that is electromagnetic spectrum, of natural objects is not as great as in case of visible or infrared. So therefore, in order to cover that area, or in order to record those variations which are present on the objects, natural objects, then bandwidth has to be increased. And therefore, compared to visible channels, we can say it has got poor spectral resolution. Depending on which sensor you are using, which is on board on different satellites, the bandwidth always indicates the spectral resolution. So narrower the bandwidth, higher the spectral resolution, and vice versa. That broader the bandwidth, lower the spectral resolution. Now temporal resolution means time between observations. How frequently your satellite is revisiting the same area again and again. So suppose a satellite overpasses on day 1 and then day 16, whereas another satellite passes on day 1 and day 8th. So the one which is passing on day 8th again, that is having higher temporal resolution. So, but again there is a trade-off. Very interestingly, like NOAA AVHRR sensor, it is covering almost the same area twice a day, because spatial resolution there is 1.1 kilometer. So if you are having low spatial resolution, then temporal resolution can be improved. So there is an inverse relation. Higher spatial resolution, lower temporal resolution. Whereas lower spatial resolution, higher temporal resolution. For example, if a sensor is having capabilities of providing data at 1 meter resolution like Iconos satellite, then the revisiting or the temporal resolution is going to be covered very less, because it covers a very small strip. In case of NOAA AVHRR, it covers about 2800 kilometer wide swath of part of the earth, whereas this Iconos having 1 meter resolution might cover just 11 kilometer swath. So it's a 2800 kilometer versus 11 kilometer. So but the temporal resolution in case of NOAA is always higher, spatial resolution is lower. In case of Iconos, the temporal resolution is very poor, but spatial resolution is very high. So there is a inverse relation between spatial resolution and temporal resolution. And the last one is the radiometric resolution, that is the precision of observations, and that we have talked 1 bit or 16 bit or 8 bit. So higher the bits, it will provide, this is what also it is called in some literature quantization. So this is if it is 6 bits versus 8 bits, definitely 8-bit image will have higher radiometric resolution than your 6-bit image, because 6-bit image can have maximum values between 0 to 63. That means total number of values for pixels are available only 64. In case of 8 bits, the total number is available 256. But these are not the accuracy. Accuracy is basically a statistical term. So do not get confused with this. This is the higher spatial resolution, higher radiometric resolution will improve the quality of your image. So that is more important, because the quality of an image will always be helpful in interpretation, and if interpretation is good, reliable, I am having high confidence in my interpretation, then I can make better inferences out of this. Now we will go in little detail about spatial resolution and see some specific examples as well. That in remote sensing, resolution means resolving power, capability to identify the presence of two adjacent objects. If they are present, I should be able to identify. So then the capability to identify the properties of two objects, which one is giving brighter signatures, which one is giving darker signatures. So an image that shows finer details is said to be finer resolution compared to the image that shows coarser details. So we say, and these are the relative terms, because when we had Landsat MSS roughly 80 meter spatial resolution, at that time it was very high resolution. Just compare 80 meter with 1.1 kilometer. But today we are talking 30 centimeter. So relatively now we are having much finer resolution than Landsat MSS. So with time we are reducing the area which is being covered. More number of pixels are being used to cover the same area and moving for higher and higher spatial resolution. But in some applications, always higher spatial resolution images are not helpful, because as I have mentioned, the higher spatial resolution images will cover a very small area or very small strip of the earth, and that means that in order to cover adjacent area I have to wait for longer. So there are always trade-off. You gain something, you lose something. So here, like the spatial resolution examples are given here. When I am having a spatial resolution 8 meter, my image might look like this. For the same area example, 4 meter, 2 meter and 1 meter. And here 10 meter, 30 meter, 80 meter resolutions examples are also shown. So in compared to 80 meter resolution, it shows a really very, when we compare 10 meter with 8 meter, it shows very poor quality, the 80 meter. But if you have not seen 10 meter, then you might be happy with the 30 meter. So this is what is happening. So size of the smallest dimension of the earth's surface over which an independent measurement can be made by the sensor, that is what is spatial resolution, expressed by the size of pixel on the ground in meters, controlled by instantaneous field of view. What is instantaneous? Because it's a 3D angle, so it is measured in radians. So it's a angular cone of visibility of sensor, determines area seen from a given altitude by a aircraft or by a sensor, and this IFOB is depend on altitude and it depend where you are looking. So if it is nadir viewing, then IOFB is having this, the angle in both the cases might be same, but the pixel size here is smaller as compared to in oblique IFOB. So this is further illustration on the IFOB or field of view. Now 3 more resolutions very quickly. Spectral resolution. Spectral resolution is a sensor, refers to the numbers, locations of spectral bands. The sensor collects the data and how wide those bands are. A good analogy may be that how many crayons are in your coloring box. Do you have 8 or 64? Of course 64 is better. So that is the advantage. And if we see the real examples with the different sensors on board of different satellites, we find like here in case of MSS 4 bands are covering this much area, whereas in case of ETM not only 4 but 5 bands are present. Similarly here the bands are very narrow, like in case of OLI, which is the latest series, and NOAA 8, the bands are narrower. So here we are having higher spectral resolution compared to Landsat TM or ETM. And spectral resolution of different sensors are given normally in black and white aerial photograph. We cover this much of the part of EM spectrum, whereas in RGB or Landsat we had 4 bands. Now we are talking hyperspectral, where we will be covering continuously the entire EM spectrum, and therefore it will have no segmentation, continuous recording one after another. So broadband versus narrowband, what is the advantage of broadband? Because collecting radiation across broader range of lambda per band and so more photons and so more energy. I have given the example in case of thermal sensors, because the energy is less and that is why the bands are broad, whereas where energy is more we can go for narrow bands. So narrow bands gives more spectral detail but has less energy, so lower signals, and then that means the lower signal to noise ratio, and more bands are possible in such situations, but more bands enables discrimination of more spectral details. That's the advantage. So if you are having more bands, our interpretations becomes much easier, but there is always trade-off in sense computer memory, processing time, consuming, and other things are there. Now temporal resolution, that we have already discussed, the time between observations, revisit time over an area, and last in this series of resolutions is radiometric resolution, the number of digital levels used to express the data collected by. So 6 bit means 64, 7 bits means 128, 8 bits 256, and is a 2 power 8, 2 power 7, 6 likewise. When we go create color images using 3 8 bits images, that means we are going for 24 bits, and we can have any color out of a palette of 16.7 million colors. And that is why the colored images are always much better than black and white image. In case of 8-bit image scenario, we will have only 256 shades of gray. Example, this is just a repetition of the same thing, that 1-bit, 2-bit, 4-bit, how they looks, and different sensors like in Cartosat 2 or Cartosat 1. I am taking example, the resolution is here, spatial resolution is 2.5 meter, here spatial resolution is 0.8. That means higher spatial resolution now we are talking. And the swath, this will control our temporal resolution. So swath is 30 and for forward and backward, but here the swath is 9 points. So it's a narrow swath. That means the poor temporal resolution. As you can see, the revisit time here is 5 days, it is 4 days. Orbits per day, 14 orbits per day of the entire Earth, here 4 or 5 orbits. And of course the altitude can also bring variations in all these. So this brings to end of the first lecture in this series, and thank you very much.